Hey, this is Steven from Legit Tech Tutorials and the Green Engineers, and welcome back to my product development series. We are talking again about the DIY metal milling machine, otherwise known as the Green Machine Mill on what I'm calling it. Its title is the Green Machine Mill. So, last day recording for the week for these for the product design series, and then we have some software design on this weekend. Another 3 videos on Zombie Alamo, and another video on Ava's game. Anyways, but again, you're probably into the looking at the mill instead of that stuff anyways, so let's go ahead and get into it. So let's see what else we could do here for the end of the week. So here we're going to open up the layout. Another thing that I wanted to do on the layout is calculate the actual X travel. So as you see, I did mess around a little bit with it on the at work. Reason being is that we have, let's look at the 11. So basically this is right now our max travel. So we have some pretty good news. So every time I start talking, my cat freaks out. It's super annoying. Okay, so mills, the 1100M, and we're comparing to the new series, not the old series. And it turns out, like we said in the other video, that the 1100M has dovetail ways still and not linear rails, as far as what I saw. Okay. Cast iron frame and table with hand scraped ways, basically. Okay, so table size 34 by 9.5. So let's compare that here. Table size 9.5. 9.5. We have 14. So we're another half. That's 10. That's 4.5. Another 4.5 inches, and 38 we're actually short, I think. 34 we're at 38.5 compared to their 34. So a little bit shorter there, but where we do make up for it is, if you notice, we are up here at pretty much max travel. So now another thing I'm wondering is maybe I should put this guy where it's in here. This will help it a little bit more for the tilt, and also I noticed that I didn't have these set as set them so that they move together, so I'll have to fix that at some point. But if we look here, we could see that we are at max position pretty much. So one of the things is spindle nose to table max clearance. So here's a spindle nose. And of course we're going to have some jaw dogs, or what do they call them? I think they're jaw dogs. Drive dogs, jaw dogs, whatever. The little blocks that go in here. I think that's the technical name, jaw dogs. Anyway, or spindle dogs, or drive dogs. I guess I'll just call them drive dogs. I forgot if that's the actual technical name for it. Anyways, distance from here to the table is 19.245 inches, and here max to table is 17 inches. So we have another 2.25 inch clearance there. And if we move this back a little bit more, we'll have even more. Down we'll have another half an inch, so I think that was 1/2 an inch. So it's 9 3/4, 19 3/4, almost 20 inches, so almost 3 inches. So almost 3 inches over the Tormach 1100M. And then spindle, so center spindle, which is this sketch here. Spindle to column clearance. So it says here, spindle center line to machine column. So again, we're on the center line to the machine column. I don't know if you can see that. Let me rotate. It is 13.945, and theirs is 11 inches. As you can see here, 11 inches and 17 inches. Spindle center line to machine column 11 inches. Max clearance 17 inches. So far we're right at kind of the size, and again we're at 820 pounds. And we're currently quite a bit under the typical system footprint, but again theirs is 1,600 pounds, so we have another 800 pounds left. But they have, looks like, a lot of housing around this thing. And they won't tell me. I might need to find out exactly how much weight the machine itself is. And so in the last one, we figured out how to get this guy in here. So another thing I was thinking about yesterday, right before I went to sleep, can't remember if I talked in the video or not, is holding this up, because obviously we need a counterweight. Usually they have a counterweight, but this is going to be against the wall or really, really close to the wall, so it doesn't, vibrate on the wall. But it'd be nice even to attach this to the sheetrock. Have some things here so we can even attach it to the sheetrock. So basically, when it vibrates, it dumps some of the vibration into the wall. We don't have any room here, and we might have an ATC over here, automatic tool changer over here. So we don't really have a lot of room here. So one of the things I was thinking is to do the exact same thing that the Skyfire CNC. Oh, no way. Do they have a... Okay, so it looks like they have a new supplier in Canada. It says Skyfire CNC Canada. That's cool. So when you type in Skyfire CNC, that's what opens up. So ours is even bigger here than the Skyfire SVM2, which is their biggest guy that they have. So that's interesting. So let's go here. Cut copper. Copper's nasty to cut, man. So yeah, we could do this. This is definitely possible. How are they holding it down on there? Oh, they're bolting it in from the bottom? Yeah, they're drilling something in there and then putting it into the bottom. Oh, they're keyboard keys. Yeah, keyboard keys. Yeah. So let's see if we can find one. Okay, so this one has a counterbalance and it has room for a counterbalance, but huh. So 10 grand pretty much. Anyways, okay, so let's go to their main website. Oh, here it is. So if we go to categories and we go down here, oh, that must be their old version. Where did I see that? Oh yeah, there's still there. It's there. So if you notice, there are shocks in there, right there, going straight up, and that's how it counterbalances the. That's how it holds up. But these have a counterbalance on the inside. The column, just like a regular one, but why do these not? Okay, yeah. So even their big boy, the mini industrial, has it. Probably because they couldn't put a big enough, and then this is a pneumatic tool changer up here. Drawbar. So basically what happens is, I don't know if you guys know how shocks work, but pretty much they stop any sort of load. So what they do with shocks are with displacement, so they counter displacement. There's things called Hooke's law, which F equals kx. K is a spring constant, and x is the displacement that you compress the spring. And so you have the k constant, and then x is the travel, right? So basically what happens is the shocks are F equals, or F is the reaction force from the shock itself, is CV. C is the constant for the shock, it's similar to that of a spring, and V is the velocity at which you are traveling. So pretty much what's going to happen is that there's going to be a force that slows down the mass until it completely stops moving. So the idea is that if you stick a shock up there, pretty much the only thing that'll cause the shock to go is if you add a force and you kind of hold it against it, right? So basically, if you change the momentum of the system, if the system stays the same weight, nothing happens. So for example, if you go and you shut the system off, the head just sits up there. It doesn't move. And that's the idea. The idea of why you have to counterbalance a machine is so that when your motor is up here working, you don't want it to have to hold the head up, right? Because the head is extremely heavy. I mean, ours here is extremely heavy. I mean, this one right here is 3,000 ounces. It's 200 pounds, that block right there. Chances are the block is not going to be as heavy as that, but you could think with motor and stuff, at least the head, we're going to have 200 something pounds. And so pretty much either you need a 200 pound block hanging over here, or you need a shock that attaches here and goes up to the head, which I think is the better of the ideas, to have a shock like this. And you can see it goes up to the top of the head, and it holds the head up. So you can see right now it's not energized, nothing's on, but the head is stationary, it doesn't fall to the table. And so pretty much what holds your head into the cut, what holds your head and thus the tool in the cut is the motor, not the counterbalance, or not the weight of the head. Theoretically, the head weight is supposed to be weightless. It's supposed to be zero force, because if there is a force, when you shut it off, it's going to come down and slam the nose onto the table. So you need to either hold it up with something that will still allow it to move when you turn it on, or something that deactivates when energized. Maybe a solenoid or some kind, a subtype. Well, it doesn't matter, because when you're running, you still have to hold it up. Because a motor, the motors that we're looking at that are 1 inch long, is not going to be able to hold a 200 or 300 pound mass and be able to move it accurately without skipping steps and be really, really accurate. So, and also 300 pounds on the ball screw, that's a lot of weight on the ball screw, right? So, and pretty much not very many of your cutting operations are going to have that type of load. So, as far as pressing in, as long as you're doing everything correctly. So this, I think, is going to be the best application, because we just don't have any other place for the counterbalance. So putting a shock there, and then obviously the shock is going to have to be, depending on how long we can find, will determine where we mount it. And basically we're going to mount it up here somewhere along this line, just like that one, and then attach it somewhere down here by the hip. Right, so pretty much as this comes down, it compresses the shock, and then obviously there's going to be a force that is going to counteract the motor. Unlike the counterweight, there is going to be a force that's going to counteract the motor as you're going down, which is again linear against the velocity times 2, one on this side, one on the other side. So what that basically is going to mean is, compared to a counterbalance, we're going to have to slow our rates way down. But it's the same thing with the counterbalance, because if you go faster than 1G of the counterbalance up and down, then obviously it's gonna, if you go up fast, or if you drop faster than 1G or go up, it's just gonna kind of suspend there, and it's gonna yank and try to rip everything apart. But highly doubt you're gonna do that. So, but even more so with the shocks is that we're gonna have to lower our feed rate down and up, because the shock is gonna be fighting the motor, because CV. So if we're trying to have a velocity, it's gonna try to keep that. It's gonna try to slow that velocity down until the velocity is 0, pretty much. Okay, so that's one thing. So I do think that will work. So we're going to have eventually a shock from here to here when we finalize how much this weight's going to be, and then we'll look at some shocks that are comparable that go up here. So we might do that now if I can't think of something to do right off the bat. So obviously we need to put something here. Oh, and then there's an issue here. So let's change that a little bit. We gotta cut that back. 0.782. I'm sure in here it looks good. And there it looks good, but over here it does not. So yeah, now it's too far there. So let's go here. There you go. Perfect. Okay. And basically what we're going to have here is we're going to have some sort of double bearing block of some type that goes in that hole right there. That's about 3/4 of an inch by 3/4 of an inch up this way. So we have the ball screw go down through here and into that block, and have another ball screw go through here and into that block. And then this guy drives this guy, and then this guy's obviously belt or chain driven to this guy and holds all that together. Okay, so one more thing, we were talking about having the total travel on this, which again I think is pretty much this 2.8. It's about 19, I'm gonna say, which compared to this guy, so we're about 1.5 inches. 1.5 inches over. Because yeah, pretty much this goes halfway here, so you lose half of this, goes to here, and when it moves the other side, you move the other half here, right? So pretty much this half here and this half here is not used. Half of this at least. So 2 times half of this is 9 inches, and 9 inches minus the 28.553 is what you get. So we are over Tormach, so that's good, by 1.5 inches of their brand new machine. And also we have what was our maximum okay, and then let's see our volume here. So this is 19 inches. Shh. Let me open up my door here. Okay, so we have 19 inches here. So I'm going to say 19.4 times 2 plus 19 is 57. Oh, but we subtract 9, I think, here. Okay, so let's do this again. 19.404 and let's do this for the last time because I know I've done this a couple times. I still don't know why this thing like freaks out so much. That is really, really close. It's 45, so it's a little bit under what we wanted, which was 48. 48. That's 2 and 1 for 8. So technically we'd get that added to the other one, so the other one was 19 and a half, so that's 21. I mean, we'll see, because another thing I want to do down there in that space is that's where my bamboo plywood's going to be. But then again, I don't think I'm going to actually store the bamboo plywood. I think once I get it, well, that's for the Eco-Base 3D printer. I think once I get it, I'm going to chop it up and then we go from there. So I don't think that I'm actually going to store the bamboo so we could have that location for that material. And then I think that we would store the full size plywood elsewhere where it's not as usable space, because right there it's pretty usable. So, and I'm thinking that could go up against the back wall. I have kind of an idea of where it would go, and where it's not in the way. And obviously that's 4 feet wide, which goes out into the room. So we can't get a car even further deeper in there because you would hit a 4-foot piece of plywood or a piece of bamboo plywood. Because again, we have a 29-inch depth to go into the room, to where you're going past the cabinets, and now you're taking up space. So, and that's 4 feet, so that's 48 inches. That's almost double that. So I'm thinking we're gonna store that elsewhere. Okay, so I haven't done a whole lot in this video. Just kind of talked about what's next and thinking, and this does look really, really good. So the next couple things are looking at these ball screws. So I'm going to talk to these guys at Highwind about their ball screws and see what's the best deal, what's the best idea for me, and then also in here, and then also how I'm going to, what are their best thoughts on supporting these guys. So I'm thinking that we're going to have something, let's in these holes, let's say, so this is 2.283, and I think this is the same. No. .283. 1.782. 1.782. Okay, and then basically it's going to be, wait a second. That's not right, what I did. That's supposed to be how tall it is. I mean, this one could basically be, 1 inch depth or whatever this is here. Because right now it's basically at the point where it's protruding out about the same amount. So let's just say that we go in here and we support around this big, actually I think this is the start of the screw. This is the bearing right here. 0.591. How far back is that? That's 1.662. 1.662. Cool. And then basically we have a bearing that goes in there. Or this could even be a bushing. We make a brass bushing or whatever. What was it, like 0.521 or something like that? Yeah, so this, as you can see, is pretty much, that's where the thread's supposed to be. 591. And let's see if that's got a close millimeter, 2 inches. 591. It's 15 millimeters. 15.01.01 is 4/10. So basically a 15 millimeter ID bearing. 15 millimeter ID bearing VXB ball bearings, 1532. 6002 pretty much it looks like. 6,000. Okay, so let's write that down. 6002 bearing for ball for 2005 ball screw. 2005, 2004, or something, whatever. Okay, so this is an open ball screw. I mean, ball bearing. Can I find a deeper one? Because how deep is this? I like to support it, the whole thing, so. 1.12. That's about 27 millimeters. I don't know if I'm going to find something like that. I mean, I could press two, one at the beginning, one at the end, pretty much. I mean, this one's 11. Nine, 32 with 9, 9, 9. 15 millimeter, 9 millimeter. So, I mean, the best we could get is R202, 15 by 35. So let's look at that, R202. Wait, what? R202, 6202 RS. 6202 RS. 6. So this is, but this is 35. Oof. Center's 15. And the height is 11, so we probably use 2 of these guys. So this is a 6202 RS bearing. And this is 35 millimeters. Bam, perfect. Looks good. Press it through. Ball screw. Bearing support. Ball screw bearing support assembly. And again, this says 27, so in this case we'll do 22, so there's just going to be a little bit of overhang in the middle. These other ones are 9 millimeters, so we can't really... I mean, you could put them together. So these are 9 millimeters, and the hole is 27 millimeters. So 9 times 3 is 27. So maybe even we could press a couple of them on this guy, and then have fully. I think that's probably overkill, but. And of course, piece of steel. And really, I haven't done this much steel, but as far as that looks okay. And there you go. Now it should be fully supported and just that piece comes out. And so basically pull it back all the way. And this guy needs to come in further. Same deal as the other one. So we can measure this. And then also we would have another one up here at the top. Man, I really don't know why he does that. That's fine. Let me just rotate it down here. There we go. And there you go. So now, I mean, we either have this one or again, we could press in three of the other ones. I mean, obviously that's like $15 worth of bearings. Because these are $3.95 a piece. And so 3 of those, you're talking 12 bucks. I mean, but for extra support, it's pretty good. So, but this has already got double support, so even this is probably okay. So we got 2 here. And then we would need another one here. Bam. There it is. And then we would need something interesting here, pretty much where 1 3/4. What time are we at? Almost 40 minutes. I mean, we haven't done a whole lot, so maybe we'll look at doing this one last time. So I'm thinking this guy be short. So pretty much what happens is half of this is pretty much where this is, and then it comes down and goes into it. Maybe it's slightly taller because again, we're not going to go all the way down. So we can look at it that maybe that one. So what was this one? This one was 1 inch, right? What was the depth of this? So how did I draw this thing? Again, I forgot. Okay, so it's this axis. 1.662. Okay, so let's do... So let's call this Z and Y joint ball screw support. So pretty much what we need is we need 1.162 down this way. So obviously it'll go down that way, but it's going to hit this way pretty much. So what I would like to do is I would like to keep this free and have this other one go about 1 inch higher, because the spindle obviously goes below 1 inch anyways, so it's not going to go all the way down to begin with. This is 1.85, so we don't really have that much room. But this is sticking up way above. So 1.85. .85 plus the difference between this and the floor. 2.5 pretty much. 4.351. So we have plenty of room. Alright, so basically what we're going to do here is we're going to do that 35 millimeters. So the sketch again, we're going to have pretty much from here to here, and we don't need to make it any longer than that. So 1.782. So let's do it from the top here. I'm already in. So was it this one? 1.782 there, I think. All right. Oh, yeah. And 2.283, 2.283, 2.283. Okay. And then if we remember, this guy is basically that depth, 1.662. And again, it's not going to be exactly that because that's maximum. Okay, so it's going to go all the way down before hitting the ground, so that's fine. I was making sure that this was tall enough. Okay, and then it's going to go that way. Oh, it's got plenty of clear. Oh no, because it's going to hit the other shaft. So we need that plus 1.662. So we need this 1.782 plus this 1.662 equals 3.444. And then down here, .283. It's not that, it's this to that. 1.782. Artificial center. Making center. Circle. .35 millimeters. Drill it. Go up here. .35 millimeters. Punch it all the way down until it goes into this other one. Looks good. Yeah, you get the idea. Okay. Basically the point where the tip of the drill goes through there. So now we're going to save this. This is going on way too long now. What are we at? 45 minutes? Yeah, 45 minutes. But we're almost done here. Oops. One. So now is where it helps to have a little bit of clearance there. I mean, we don't have a lot, so if you look down, you should see just a little bit of space. But I think these are actually spaced out where that will clear. Nope. Well, that's 35 millimeters, right? I think it was like 35 millimeters. No, it was 15 millimeters. 15 millimeters. Oh yeah, it'll clear. So it doesn't even have to be as long as it is. But anyways, ooh, that's another thing. How am I going to get it down at the bottom? Let's do this. Specs, section analysis, origin. Turn off the body. This body. Turn back on. New joint. I think that's the bottom. Question is how exactly do I even press that in there? That's a good question. I mean, I pretty much have to push that in first because you can't see otherwise. But cool. And there you go. Alright, let's drop it in, call the video over. So beautiful. And there it is. Alright, so right before we leave here, let's go close this. Let's do properties. 1,3550 divided by 16. We're at 846, so we added another 20 pounds. Alright, so this has been Steven from Legit Tech Tutorials and the Green Engineers. Thank you guys so much for staying in with this 48-minute video. I'm going to go ahead and upload this right now. Thank you guys so much for watching, and I'll catch you next week for more product design series for this project. Take it easy. Peace.